All right, geometry, lesson 45. We're talking about the introduction to coordinate proofs. Basically, this is an algebraic way of looking at geometric figures on a coordinate plane. So a coordinate proof is a style of proof that uses coordinate geometry and algebra at the same time. I know a lot of excitement about this. In a coordinate proof, a diagram is used. It's placed on a coordinate plane. So it's not a two-column proof, a paragraph proof, or a flow chart. It's actually just a visual. Okay. Let's see. Figures can be placed anywhere on the plane, but in order to make your life a whole lot simpler, there's specific locations that make it easier to understand. Okay. It's usually easiest to place one side on an axis or to place one vertex at the origin. What you see down here is a list of examples given different shapes. You know, if you were going to place them somewhere and it told you a triangle, probably the easiest place is to put a side on an axis and a vertex at the origin, okay, as much as you can. So if you get something like a square, putting one vertex at the origin and two sides on either axis, and keeping it, I would say, in the first quadrant. You could put it in any quadrant, but putting it in that first quadrant is going to keep everything positive, and in terms of how you think about things, it's going to keep it in simplest form. Sometimes you can't do that. You know, here you've got a rectangle. It may spread across two axes, or we could slide that thing all the way over. Just looking at different ways of looking at it, you could put a triangle with a vertex at the origin, and basically it's showing it in contrast to the first triangle that you see over here furthest to the left. When a figure is placed in a convenient position on the coordinate plane, the equations and values used in a proof are going to be easier to work with. So what you're seeing down here are examples of convenient placement for common figures. You don't have to put them there, it just makes it way more convenient to work with. So sometimes a figure's dimensions are unknown. They'll give you a variable that represents the y value of a coordinate, or a variable that represents the x coordinate of a point, a position. When placing a figure with unknown dimensions on the coordinate plane, you want to pick those convenient positions and label the vertices of the figure using information that's given in the problem. When you assign variable coordinates to a figure used in a proof, remember that the values you choose have to apply to all cases. So when the dimensions of a figure are not given, variables have to be used to ensure the proof is valid for a figure of any size. And that's it for that. Let's look at some questions here. Okay, so we start right off the bat, and they go ahead and they give you a rhombus. We know certain things about a rhombus, and so whenever they tell you a rhombus, they don't tell you that, I still can't draw on this, they don't tell you that just for kicks and giggles, right? They tell you a rhombus because we know certain specific things about a rhombus. We know that, what do we know about a rhombus? Let's list a couple of things. Do we know anything about a rhombus? It's a parallelogram, which means we know four things about a rhombus then, right? Because we know four things about all parallelograms. We know that opposite sides are congruent. We know that opposite sides are parallel. We know things about its angles. We know that consecutive angles are supplementary. We know opposite angles are congruent. Consecutive angles, so like you add up to equal 180. Now a rhombus is specific inside of parallelograms, meaning that all four sides are congruent. Okay, we know that the diagonals are perpendicular, right? We know a lot of different things. We're not necessarily going to use all of those things here, but we're going to use some of those things. We're going to use some of the stuff that we know about parallelograms. Okay, and give me a second. I want to see if I can figure out how or why this isn't letting me draw on it. Okay, we didn't get it figured out. But Michael, you brought up a good point. We know that the y value, that vertical movement, is going to remain the same. So that in this position that we're looking at, right, it's going to remain D, right? Because D is the y-coordinate of my upper left vertex, right? So what conclusion you come to is that on my lower right vertex, the x-coordinate was C, but we know that our upper right coordinate can't have just C movement. It goes at least C, but it goes beyond that. We have to figure out how far it goes. Well, because the line that goes from 0, 0 to AD is parallel to the line that goes from C0 to our unknown, right? It has to have the same rise over run, right? So it's going to rise that D, but it's going to run also A. So imagining that A was, say, 3, and C over here was 4. Well, that would be 3 plus 4, so I would get 7. So we're just taking it back to an unknown sense. So I should get C plus A or A plus C, and then D for my y coordinate. So I should get B for an answer there. Does that make sense? Okay. Question or just stretching? Stretching. All right. Some of these are going to be hard to draw because I can't actually draw them. Okay. Let's see. Let's, you know what? Honestly, at this point, there's really not that many questions in this. Let's look at some questions that are in your homework. See if there's anything from lesson 45 in your homework that we can work out, something I can actually draw on and write up. Let's see. What are your assignment numbers? 9 through 19. So like question number 9, right? Question number 9 comes from lesson 45. So even if we just did question number 9, right, that's going to help us out at least a little bit. Okay, so first thing I'm going to do is I'm going to draw a coordinate grid. And granted, if you want to use graph paper back there, you're certainly free and welcome to use that. I'm going to go ahead and kind of draw this up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see how we go from there. Number 9, we've got JKLM. We got vertices at 0, 0. Okay, so nice, neat spot right there. 2, 2. So we got another one right there. We've got X, Y, and 5, 0. So 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, so notice that they do tell me that it's a parallelogram, right? Well, it's not going to be a rhombus because in a rhombus all sides are equal length. So you can tell that from J to K is not the same distance as from J to M, right? But it is a parallelogram, right? It's just a parallelogram. No, it's not a rectangular rhombus because a rectangle is its own separate thing. Okay, so because it's a parallelogram, remember that my slope, the opposite sides have to be parallel, right? Okay, so I'm using what I know about a parallelogram. So let's try to find the slope from J to K, and that same slope should exist from M to L. Does that make sense? Well, let's see. So our slope is, let's see, let's do 2 minus 0 over 2 minus 0. So yeah, you're getting 2 over 2, which is a slope of 1, right? So if I'm going from 5, you know, I'm going to go up 1 over 1, up 1 over 1. So, you know, we're going to go that same distance. I should wind up actually a little bit better than that though. Okay, up 1 over 1, up 1 over 1. Okay, keeping in mind that I'm hand drawing that, so that's why it doesn't look very good. Let's see if we can't fix that up a little bit. Now that coordinate right there should be the coordinate for L. Okay, well what are those coordinates? Notice that from J to K I went to the right 2, up 2. So for M I'm going to the right 2. So that's going to take me to 7 up 2 is 2. So I should get 7, 2. Okay? Yeah, so did I. Yep.